In this video here, we're going to take a look at the Maclaurin series. Now, many of the functions that we've come across so far in A-level maths can be written as an infinite sum of terms. And you'll have seen examples of this when looking at the binomial expansion. So for example then, 1 all over 1 minus x is equal to 1 plus x squared plus x cubed plus so on and so on. This is just an infinite sum of terms, right? And this here then is valid for x between minus 1 and 1. Now, another way that we can express functions such as this as an infinite sum of terms is by using what's known as the Maclaurin series. So let's have a look then at the Maclaurin series in more detail. Now, the Maclaurin series expansion of a function f of x is given by the following here. So f of x is equal to f of 0 plus f prime of 0 times x plus f prime of 0 all over 2 factorial times x squared plus so on and so on. You can easily see then how this result generalizes. Now the series is valid given that f of 0, f prime of 0, f prime of 0, and then the nth degree of the function f at 0 all have finite values. Now you also need to be aware that the Maclaurin series is only valid for values of x that lead to a convergent series. And it's also just worth mentioning here that a number of useful Maclaurin series expansions are given to you within the formula book, such as sin x, cos x, and e to the x, but it is important that you also know how to derive these yourself, because sometimes you might be asked to do that as part of an exam question. Okay? And finally then, the Maclaurin series relies heavily on differentiation, so just ensure then that your differentiation skills from A-level maths are up to scratch. So there we have it. That concludes this introduction here to the Maclaurin series. It is just worth pointing out that we can actually derive this result here from the Maclaurin series, but I'm not going to cover that for this video here. I'll do that as a separate members video. Okay. As I mentioned, then that concludes this introduction here to the Maclaurin series. Let's just work through a couple of practice questions. So let's just get started then with question 1 here. So for the first part of question 1 here, all it asks us to do is find the first forward non-zero terms in the Maclaurin series of sin x. So to get us started then with part A here, let's just begin by stating the Maclaurin series for some function f of x. So the Maclaurin series here for some function f of x is given as follows. So we get f of 0, so f of 0 plus f prime of 0 times by x plus f prime of 0 all over 2 factorial, and we times this by x squared, and so on, so on. And you can see how this result here will just keep extending, right? So clearly what we need here then is a number of derivatives, right? So we start with f of x here, and in this case here, f of x will be equal to sin x. And from here then, we need f prime of x, f prime of x, so on and so on. And what I'm hoping for here then is that eventually we can spot a pattern. So f prime of x, f prime of x, so on and so on. Now at each stage, what we also need to do here is evaluate these for x equals 0. So f of 0 here would simply be sin of 0, which would give us 0. Okay, let's just keep going here then. So f prime of x, so differentiate sin x with respect to x, that just gives us cos x. So we get cos x there. And again, don't forget to evaluate this at x equals 0. So f prime of 0 is equal to 1. F prime of x, that would give us minus sin x here. So f prime of 0 would give us 0. So for the third derivative here then, this is equal to minus cos x. And if we evaluate this here then as 0, what we get here then is minus 1. Now for the fourth derivative then, what do we get here? Well, just notice now if we differentiate minus cos x, we get sin x. And as you can see then, the pattern will now just repeat here. Okay. So the fourth derivative here, 0, is just equal to 0, right? This pattern there will just repeat here. Okay. So at this point here then, we actually now have everything that we need then to find the first four non-zero terms in the Maclaurin series of sine x. So therefore, f of x here, so f of x is equal to, so we get f of 0. So f of 0 is just 0, right? So I'll write it down anyway, but normally we wouldn't include that. We'd just leave it. So 0. We then have f prime of 0, so that's 1 times by x. So plus 1 times by x there. Okay, let's keep going here. So as you can see now, for the third term here, okay, f prime prime of 0 over 2 factorial times x squared, because f prime prime of 0 is just 0, this term here will be 0, right? That's one of our 0 terms here. So this one would just disappear. If we keep going then, my next one here would be minus 1 over, so when it gets to minus 1 here, this will now be over 3 factorial here. We just keep going along, right? So it's then 3 factorial, 4 factorial, 5 factorial, so on and so on. As you can see then, for the even factorials here, they will all be part of the 0 pattern, right? So 0, 0, 0, so on and so on. So for my next term then, what I get here is minus, I get minus 1. So minus 1 over 3 factorial, and we then times that by x cubed. Okay, let's keep going here. So now the next one then would be 0. So in fact, let me just go back a little bit because I didn't include it previously. So before this here, there is a 0. So I'll include it anyway. Obviously, you wouldn't really include it as such. It just obviously disappears. So 0, as we then mentioned, we then get plus, we get minus 1 over 3 factorial x cubed. Let's keep going here. So the next term now would be 0. We then get 0. The next term, then we now get 1. So you can see here it just alternates. So 1 over 5 factorial. Now, so this would have been 4 factorial. This would have been 2 factorial, so on and so on. X to the 5. The next term here will be 0. So plus 0. And then finally here, the next one would again be minus 1 over 7 factorial times x to the 7. Okay. Let's just quickly count here. How many non-zero terms do we have? We've got 1, 2, 3, 4. Perfect. That gives us the first 4 non-zero terms in the Maclaurin series of sine x. If we just simplify here then, f of x, this is for sine x then, is equal to 1 times x, that's just x there, minus 1 over 3 factorial times x cubed, so I just get minus x cubed over 3 factorial. We then get x to the 5 over 5 factorial. So x to the 5 over 5 factorial. We then get minus x to the 7 over 7 factorial. Like so. This just keeps going on and on. And this here then gives us the first 4 non-zero terms in the Maclaurin series of sine x. So now let's have a go then at part B here. So that's the solution to part A. So moving on to part B then, let me just do this in a different color. Let's just do it in green here, just so you can differentiate between the two different parts of the question. In fact, I'll box it off just ever so slightly here. Like so, we shouldn't need too much room here for part B. So for part B then, it just says using the first 2 terms of the series, find an approximation for sine of 5 degrees, giving your answer to 3 significant figures. So for sine of 5 degrees here, so for sine of 5 degrees, so the first thing to note here then is we need to be working in radians here, right? We've differentiated trigonometric functions here, so we need to be working in radians. So sine of 5 degrees, this is the same then as sine of pi over 36. Okay, like so. So for sine of 5 degrees here, this will be approximately, so using the first 2 terms here, so we're going to use these 2 terms here. So this term here and this term here. So we get x. So x here is just pi over 36. We get pi over 36 minus then, so x cubed, so that's going to be pi over 36 cubed. And then we times it by minus 1 over 6 here, because 3 factorial is just 6, right? So I get minus 1 over 6, minus 1 over 6 here. This is the 1 over 3 factorial. And then we times it by x cubed here. where x is pi over 36. So pi over 36 cubed, like so. So to finish with here then, all we need to do now is just put this into our calculator. If you do this correctly then, obviously just make sure that you give your answer to 3 significant figures. What you should get here then is 0.0872. Okay? 23 SF there. And there we have it. So that's the solution to part B and the solution to question 1. So let's just have a go now at the very last question here, question 2. So for this question then, it says using the series expansions of sin x and cos x show that 2x cos x minus sin x is equal to x minus 5 over 6 x cubed plus 3 over 40 x to the 5 minus so on and so on. So as the question says here, right, we're just going to use the series expansions of sin x and cos x. So we don't need to actually derive the Maclaurin series expansions of sin x and cos x ourselves. All we need to do then is just use the formula book. So for sin x here, this is given as follows. So it's x minus, so we get x cubed over 3 factorial. So x cubed over 3 factorial plus x to the 5 over 5 factorial, so on and so on. Okay. Now for cosine x, this is given as follows. So we get 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial. Okay. And again, that just keeps going on and on. So to begin with then, let's deal with the 2x cos x here. So for 2x cos x, all we simply do here is we take the series expansion for cosine x here on the right hand side, and we times that by 2x. Okay, so we get 2x times by the series expansion here. So we get 1 minus x squared over 2 factorial. So 2 factorial is 2. So 1 minus x squared over 2 there. We then have x to the 4 over 4 factorial. So 4 factorial is 24 there. So plus x to the 4 over 24. And that just keeps going on and on, right? Like so. So if we expand this out here then, what do we get? We get 2x times by 1, so that's 2x there. Nice and straightforward. We now have 2x times minus x squared over 2. So the 2's will just cancel here, and I get left with minus x cubed. And then finally here we have x to the 4 over 24 times by 2x here. So what I'm going to get here then is x to the 5, so plus x to the 5 over 12. Okay, so this here then is 2x cos x once we expand it out like so. This will just keep going on and on, right? But all we're really concerned about is going up to x to the 5 terms. So we now subtract sin x here, which is this series expansion here. So altogether then, what I've got here is 2x cos x minus sin x. So I've got this here. So 2x minus x cubed plus x to the 5 over 12 minus then sin x here. So sin x then is given as x minus x cubed over 3 factorial, so on and so on. So minus x here. So 3 factorial is 6 there. I get minus x cubed over 6 minus x cubed over 6. And then 5 factorial here is 120. So we get x to the 5. So x to the 5 over 120. Okay. Like so there. So to finish with then, let's just simplify this, right? So 2x minus x here just gives us x. Perfect. That's what we require here. So that's a good start, right? If we didn't get that, I'd be a little bit worried. So let's just keep going then. So I've now got minus x cubed here minus x cubed over 6. So this is just the same then as minus 1 plus 1 over 6. So altogether then, we get minus 5 over 6 there. So minus 5 over 6 x cubed. Okay, don't forget the x cubed, of course. And then finally here, we have 1 over 12 x to the 5 minus 1 over 120 x to the 5 here. So once you simplify that then, what we get here is 3 over 40 So 3 over 40 x to the 5 there, exactly as we require. So as required there, and question complete. So there we have it. That gives us the solution then to the very last question, question 2. And that brings us to the end then of this video here on the Maclaurin series.